Good afternoon, everyone. And thank you, Edouard, for inviting me to speak here today. So in some ways, my job's a bit easier because they've had several really interesting talks about the ocean system and overturning and the carbon cycle and so on, modeling. In some ways, it also makes maybe what I'm going to say completely redundant, but hopefully not entirely. From a sort of paleoclimatological perspective, the ocean at zero order is often thought of as just as a carbonate factory. So for the closure of the carbon cycle on the very long time scales, which fortunately I didn't talk about, and I won't either really, you can think of the ocean as just a carbonate factory. There's CO2 coming out of volcanism and so on into the atmosphere. It's the main source. This acidifies rainwater, this erodes mountains and consumes the CO2. The products of that goes into the ocean, and the organisms defy thermodynamics to turn that into sediments that then are output, so it closes the loop. Very simple and important part of the system on long time scales. But on shorter time scales, as you can see in the cartoon on the right-hand side there, and as we've heard a lot about this morning, due to energy inputs, heating and cooling, and tides, in particular, and winds, imparting momentum on the ocean and creating density gradients and so on, there is a lot of dynamism within the ocean, and because of the presence of biology as well, you get very interesting and important aspects that emerge, where the ocean is really playing an important role as a reservoir and a transporter of heat and carbon in particular. Okay, so that's the thing we're dealing with, and we've heard a lot about that already this morning. I think this plot here, I've taken this from the book by Rick Williams and Mick Follows, which is a nice textbook. They've got some nice color plates, and this is showing an overlay of chlorophyll. So this is squishy stuff, biology and chemistry, if you like, and then flow speed or kinetic energy, if you like. So physics in the white colors, if you like, and it's showing what we saw earlier. The fact that this conveyor belt is actually composed of eddies and filaments and all sorts of fine scale structures. And it also emphasizes that biology and its activity is strongly correlated with many of those features. Not spot on, but the two are there playing important roles that are somehow connected. And as Fortuna and others have talked about, it's those two things together which really bring the ocean's role in the climate system to the fore. So dynamics, if you like, combined with chemistry and biology gives you tracer fields. It produces the patterns of carbon-13 and oxygen and all that stuff that we've been hearing a lot about, and these are just some examples of plots for the Atlantic Ocean only for different things. So this is temperature, potential temperature, salinity, density, silica, phosphate, and DIC. So there's some nutrients over here, some macronutrients, phosphate and silica, DIC, and you can see some characteristic patterns. They show you where water is flowing, perhaps. But the key thing is that they're not just telling you where water is flowing, they're telling you about how the flow of the water interacts with chemical and biological processes, which are non-conservative processes. So, and this makes, well, this has two aspects, two things come out of this in terms of reconstructing past and even current circulation fields. The one thing is that even if you know, so for example, here's a model output of a transport. This is actually something from the Byrne model that I've snitched from some work that Fortuna and his colleagues have done. Here's a transport field in Sverdrup, so as we've heard about in the morning. So there's a flow clockwise where the red is, and the other way where the blue is in the Atlantic. This is from a computer model. Okay, we know what the transport is. What that does to phosphate, for example, is to produce this field. The field is not the transport, and I guess that's an obvious point, but I think it's a really important one to make, that what we're typically looking at, and the point was made this morning actually very well by several speakers, what we're typically looking at is not transport, but chemical fields, and they're not the same thing, they're not identical. One emerges from the other. Okay, so here's phosphate. You can see there's obviously a lot of it over here in the South Atlantic. There's less of it in the North Atlantic, and as you've seen many plots by now of this penetration, if you like, of low phosphate, in this case, water through the Atlantic Meridional Overturning circulation, you can see it in that picture. And then, of course, a further key point is that if you were to change the transport, so this is the anomaly in transport that we see here versus some other baseline state. Okay, so there's a reduction, if you like, in the Atlantic in this model simulation in that clockwise flow. That produces a change in the phosphate field. Okay, this is pretty obvious stuff, pretty simple. But the point is that this is the sort of stuff that we're dealing with, especially when we're trying to reconstruct past ocean circulation states, we are looking at tracer fields at best, ideally, and from that trying to infer the dynamics and biology and the interaction of the two. And what we typically are doing is taking a few sites, so these dots here are maybe hypothetical core locations, places where we're lucky enough to get some data that we think we can trust, and we measure, in this case, we imagine we can measure phosphate. Wouldn't that be nice? In the past, and we have some data, okay, plotted against water depth, and we can see that there are clearly some changes relative to what it looks like today at those same core locations. You can get more data, and eventually you can reconstruct some kind of a profile of phosphate in the past. Okay, this is straightforward stuff, but it's an important point, I think, to distinguish what we measure versus what we're after. We're measuring, for example, phosphate, and even in an ideal world, at a few locations scattered around the ocean to infer something that the ocean dynamics has produced somehow, taking into account other things that we also don't know, such as biology. So this is our modus operandi. This is what we can do, okay, to reconstruct past states. We hope to get some dots like that. And then the question arises, what would you want to measure, okay, and given what you'd measure, what would you be able to infer exactly at best? Okay, so a lot of the time we're thinking about transport, the overturning circulation, and so on and so forth. And as we heard very eloquently this morning, this is not something that's easy to reconstruct, even in the modern ocean. So this is an example for on the left-hand side. The pointer isn't working very well, I think. On your left-hand side are some estimates of mass transports in the ocean from Ganasho and Wunsch in 2000, and you can see it's quite blocky, if you like, quite granular view of transports in the ocean. We've seen other better examples of more localized regions, of course, this morning, but for the global ocean, this is one example, and this is inferred with difficulty from principles of conservation of salt and nutrients, phosphate and oxygen and so on in the ocean, and as well as some constraints from direct current meters. And the point here, of course, is that this is a difficult thing to do even in the modern ocean. So how would we infer transports in the past? Well, for the most part, we don't. And I would argue that actually flow rates aren't necessarily the most informative and interesting thing anyways for many of our purposes. What we usually really want to know is how the ocean has changed, if you like, and what that impact might have been on heat and carbon transports in particular, including, for example, carbon sequestration, as we've heard a bit about just a minute ago. And for these purposes specifically, reconstructing biogeochemical fingerprints, chemical anomalies, changes at different places in the ocean are actually very informative and very useful. Okay, so it is true, and amongst consenting adults, we should all be aware, especially amongst paleoceanographers, we're not reconstructing transport rates, we're not reconstructing flow and so on and so forth, or where the Gulf Stream is and all that kind of stuff, or how strong it is and so on. We might be measuring instead chemical anomalies that emerge from changes in the ocean circulation. That's quite robust. If you see a huge change in the Atlantic phosphate field, something must have changed. And so on the one hand, it's sort of woolly, but on the other hand, it's really quite robust and gives us some important information. So, for example, again, these are model examples in an ideal model world. On the left-hand side, you've got a plot of, again, for the Atlantic in this model simulation of the true age, what Fortunato was talking about. How long is the water spent below the surface? So it goes to the surface, clock starts at 0, and then it moves around, and the clock's ticking. And what is the age of that water, basically? That's on the left-hand side. And on the right-hand side, you can see how much respired carbon is there. So how much biologically fixed carbon in the surface ocean has rained down and been remineralized, how much has accumulated, and no surprises, the longer the water has been hanging about in the ocean interior, the more respired carbon it has accumulated. Okay, so the point being, if you were to be able to reconstruct something like the time scale of turnover of the ocean, you might be able to say something about respired carbon, which would otherwise be quite hard to reconstruct directly. Okay, so much so for the principles and so on, sort of housekeeping, if you like, but I think important nonetheless. The question then emerges how you can reconstruct past changes in chemistry. So I made the point that we can't reconstruct transports, but we can reconstruct chemical anomalies in particular. But then the question emerges, how do you get those? How do you get the past ocean chemistry? So we're after some aspect of the seawater, and usually what we're doing is using organisms that have lived have grown shells in particular, or other body parts, usually shells, in that seawater and inherited some chemical fingerprint. Those things then fall to the bottom of the ocean when they die, and they accumulate in the sediments, and we go out in ships and take long cores of the mud, penetrating down in depth, so that depth is time because it takes time for sediment to pile up. Okay, then we get little blobs of mud in core slabs and that kind of thing. And then we chop the mud up. Every centimeter is, I don't know how many years, a certain amount of time. We wash it to get the coarse fraction, so all the clays and stuff are removed. And you end up with often with a sand like this, a fine sand. This is from, I can't quite see from the picture, I think it's from the Southern Ocean. And it's mainly composed of foraminifera, which are these calcareous microfauna, fossils in this case. Okay, little tiny shells. They're sort of sand-sized grains, and then you look at them under the microscope. You pick them by hand, one by one, looking for nice, beautiful examples of a given species. Okay, you collect them, hours and hours of work. You then purify them in the laboratory and do various things and bung them into a mass spectrometer or whatever you like, and out comes, 3 significant digits. Okay, and so this is, and we're always pushing at measuring fewer and fewer of these to get more and more significant digits at the same time, which is all very well and important for some things, but one must bear in mind this whole process. There's a great deal of sanitization that goes on in producing very precise numbers, when in fact that number reflects, in this case, some isotopic composition of an accumulation of organisms that some human individual perceived as being the best ones to pick out of something that was washed and slopped around in a tray and so on and so forth. So there are many things that intervene between what we measure and what we're trying to get at. And it's maybe amazing that we can do anything, but we can actually. When you look at the patterns of data, they emerge, as Fortunat showed, for example, they really are quite clear and quite impressive. So what ocean circulation proxies are there? I can't go through all of them, and luckily I don't have to because Edouard has already introduced many of them, and they've been talked about quite a bit already. But as I said, the process is to take a sediment core. Depth is time. We take these cores out of their core liners, slice them up, wash them, get this stuff. This is an example of some sediments from off the coast of Portugal, actually. And as Edouard pointed out, these are actually from Heinrich I off on the Iberian margin. You can see big bits of sand. This is quartz and feldspars and other things. Those things could only get there by icebergs bringing them and melting and dropping the sand. Okay, so you have evidence of ice rafting. You have some microfossils that were bottom dwelling, some that are surface dwelling. That means that the chemistry of this guy is going to tell you about the bottom of the ocean, whereas the chemistry of this one, which was co-deposited and lived at approximately the same time, tells you about the surface ocean. Okay, so you can get spatially resolved data even from the bottom of the ocean. I know many of you already know this, I'm sure, but it's good to go through this in complete detail. And then some examples which you've seen already, things like carbon-13, protactinium-thorium ratio, sortable silt grain size, neodymium, uranium. Bob's your uncle. You can measure anything you like, color, zirconium to calcium ratios, anything you can think of, as long as you can figure out what it might mean is fair game. Okay, so, but for the ocean circulation, these are typically the ones that we're often thinking about. And again, it's important to realize, and I think many practitioners even become sort of a bit lax with what they're referring to. So we often talk about, you might see a time series of any one of these things and talk about ocean circulation. But of course, none of them tells you about mass transport or circulation per se. They'll tell you about, did the water come, a lot of the water come from the Labrador Sea, or was there something able to sort it, and or was there a change in the sediment source? Or was there poor or strong gas exchange and or more nutrients being put in, and so on and so forth? Was there great opal export at the time, or an integrated mass flux across the water column? So they're all complicated. None of them are straightforward and direct proxies for one thing, especially not transport. But I will highlight one here, radiocarbon. You've already heard a lot about it. And for my money, radiocarbon is probably one of the more straightforward proxies. It's complex, but all the complexities are on the surface, I think. So as you've seen and heard already, radiocarbon is produced in the atmosphere. Okay, it then participates in the carbon cycle as a sort of radioactive CO2, if you like, or carbon species. It therefore dissolves in the ocean quite readily, depending on ocean chemistry and PCO2 differences and so on. It's taken up by organisms which record the radiocarbon signature of the water that they're in, which is very helpful because we can then use those to infer what it was in the past. And a parcel of water will then move around, and as it moves away from the source of new radiocarbon, will start to lose its radiocarbon, which will halve approximately every 5,700 years or 6,000 years on average. Okay? And as a result of all this, the radiocarbon activity of a parcel of water will be very useful in telling us what, not what the transport time was, but what was the turnover time with respect to the atmosphere of the carbon in that water. And that's a useful thing to know about if you want to know about ocean circulation, and in particular the impact of ocean circulation on carbon cycling. So radiocarbon isn't really a transport tracer, and everyone should be aware of this when applying it. It's a carbon cycle tracer. It's a carbon tracer, if you like, tracking the movement and the time scale for movement of carbon in the Earth's environment. Okay, so radiocarbon is a particularly useful one, and I wanted to highlight it, but it's already been explained a little bit before, which is very useful. I'm going to come back to some data later on radiocarbon. Okay, so far so good. That's all the motherhood and apple pie part. When we look back in the past, what can we know? Well, here's 1 million years of, billion years of Earth history, sort of cartoon plot really showing upward is warm and or less ice, and downward is colder and or more ice, and it's on a log time scale. So you've got more detail on the far side, and everything's sort of squished up on the right-hand side. And my only point here is to illustrate that there's a vast, and this is just part of Earth's history, a vast array of different natural climate experiments to think about, from snowball Earth episodes and bolide impacts and hyperthermals and the onset of Antarctic glaciation and weird warm periods thereafter, periods of quite stable warm climate with CO2 about like what we have today, with no Greenland ice sheet, intense glacial cycles. There's all sorts of stuff to look at, and I'm not going to go over ocean circulation changes for all these things. I'm going to focus, perhaps a little bit boringly, on the last, or certain aspects of the last million years or so, these glacial interglacial cycles where you had the waxing and waning of really large ice sheets. So this is a blow-up of the last 500,000 years, times going from towards me to the left. And up on the top here, you've got some records of approximately sea level, okay, global average eustatic sea level, so volume equivalent sea level changes. And atmospheric CO2, and the CO2 is from ice core records. The sea level is from isotopic records in marine sediments. I won't go into that in detail. But the point here is just to show that you've got these huge changes in ice volume, 3,000 meters over North America, for example, producing, kind of 120 meters equivalent of sea level change between a glacial maximum like this or an interglacial, accompanied by swings in atmospheric CO2. And it's well established by now that the pacing, the timing of these quite important global upheavals in climate, the timing at least, was determined or influenced significantly by changes in solar radiation distributed around the seasons, the annual cycle, and latitude, so insolation as it's called. So here is showing the intensity of northern hemisphere summers, which is usually taken as a proxy for something that might have been pacing ice melt. Okay, so there's an astronomical forcing, a solar forcing, if you like, a seasonality, that's pacing these huge climate changes. And the only way, this is a whole fascinating topic, the only way it can do that is through nonlinear feedbacks within the Earth system, including in particular the ice sheet changes themselves and atmospheric CO2. Okay, and in this context, I'm going to focus on the last glacial maximum. It's quite interesting to know and use this as an example to understand why CO2 could have been low, okay, and therefore what processes could have helped. Ultimately, I'm not going to go into this, but ultimately the goal for many paleoclimatologists would be to link this external forcing to internal feedbacks that cause CO2 and ice sheets to change in nonlinear ways. Okay, so all of that to say my focus is on the last glacial maximum, and I'm going to try to tell you a bit about some data reconstructions of past ocean circulation. So now I'm coming back to radiocarbon data. These are data that we put together some years ago and recently redone this, and it hasn't changed the picture that much. So in each panel, you've got a different ocean basin. There's the Atlantic, the Pacific in the middle, and then the southern high latitudes of all basins. So the Southern Ocean, basically. And the dotted dashed lines, are the modern profiles, and the open dots are the modern radiocarbon data from the modern ocean, from the various core locations, okay, in each basin. Okay? And then the solid lines and the solid filled symbols are the last glacial maximum radiocarbon data at the same core locations. And so you can see across the board there's an increase in the radiocarbon ages, or equivalently a decrease in the radiocarbon activity of the seawater, we think, at those locations all over the place. There's quite a lot of noise, okay? Physical oceanographers will look at this and think it's a nightmare. For paleoceanographers, it's not too bad. It's pretty good, actually, for what we deal with. There's definitely a bias of the solid lines versus the dashed lines. That's the key point. So everywhere got older. There are some interesting patterns. The solid lines actually aren't just best fits. They're kind of arbitrarily determined sort of abyssal recipe lines. So it's kind of like a vective diffusion line to see if, to see if we could try to get some information in a very simplistic way about how the ocean circulation might have changed. And nothing too informative comes out of that, except the trivial outcome that you have to have a slower turnover time, a slower mixing time across the column to get that bulge. But one interesting thing is that in the Atlantic, it's harder actually to fit the upper ocean. The radiocarbon ages are a bit younger than you'd expect for a simple sort of diffusive ocean that fits the bottom, where it is much older. And that is a hint at what Fortuna actually just pointed out, that the upper ocean in the Atlantic seems to have been different. There's a chemical divide. It's been talked about for many, many years. But it seems to be present in many data sets. And I think here the mismatch between the solid line and the data is indicative that the upper Atlantic at the last glacial maximum still had some turnover that's quite effective. But overall, an older ocean, right? A less vigorously turning over ocean. And hopefully, if you listen to what I said earlier, you'll all be sort of squirming in your seat saying, what's that guy talking about? He told us earlier that you can't infer water transport times from radiocarbon. You're absolutely right. What I mean to say is a slower turnover of the carbon in the ocean. Okay? And that's an important point, which I'll come back to later, I hope. So here's just a schematic, the same data shown in planned, in sort of zonal average view, if you like. The top is showing benthic atmosphere offsets. So this is the radiocarbon age of the water versus the atmosphere at that time. Okay, we have to have some way of normalizing the radiocarbon activity. You can do it to the local surface ocean, as Fortunat showed you, which is useful if you want to be agnostic about what the surface ocean and atmosphere were doing. But in this case, you want to normalize everything to the same reference, which is the atmosphere, well mixed. Okay, so it's giving us an idea of not of the transport time, once again, but of the isotopic deviation, if you like, the isotopic disequilibrium between that parcel, the DIC and that parcel of water and the contemporary atmosphere. Okay, so the top is showing the age offsets, okay, for the Atlantic on one side and the Indo-Pacific, really the Pacific on the other side, water depth versus latitude, and then with the south is in the middle in both cases. And then below is just the offsets from modern. And the average age offset, using these, we've basically done an interpolation that we hope is a bit more sophisticated than just taking an average of the data. And that's important because we don't have, and it's often misleading when we see plots like this, you have a sort of square ocean with dots all over the place within the middle of the ocean, but all of those dots come from the outer surface, the bottom of the ocean. We don't really know what's going on in the middle of the ocean because there's no seafloor there, right? So, and that's an interesting problem that we can't really get around very easily. So what we've done is try to interpolate based on those points that we have around the skin of the sediment seawater interface to try to interpolate in an oceanographically set plausible way what the interior would be doing, and on that basis infer an average. And that's important because not every point will count equally to the global average. If you have a few points in the deep North Pacific, as Fortunat pointed out, the ocean is the Pacific. They're going to count a lot more for the inventory than some point in the Nordic Seas, for example. Even if you have 50 points in the Nordic Seas, they should count less for the average than 2 in the North Pacific. So that's why we've done an interpolation. And the average change is 700, 800 years. Which is, okay, who cares? That's interesting. For one thing, it's interesting. This agrees almost spot on with what Fortunat just showed in his modeling study. You might say that's no surprise because he's tuned it to the same data. It's not exactly the same data set, actually, but it's about that. He had 500 years, but you'll remember that was the difference between the surface and the deep that increased by 500 years in his models. The surface, we think, based on just PCO2 changes, must have changed by 250, so that gives you about the same change. Okay, why do we care about that number? who cares if it's 500 or 300 or 800? Well, the answer is again, what Fortune already talked about a little bit, which is that the age of, so this is a two-box view of the ocean. It's effectively a zero-dimensional model. And the surface of the ocean we can think of as being in tune with the atmosphere, exchanging CO2 at some efficiency with the atmosphere. There's biology up here that's fixing CO2, okay? That stuff sinks down to the bottom of the ocean. This is a pump, if you like, of carbon, a biological pump that's fixing carbon on the surface and sending it down to the bottom. Fixing carbon on the surface, sending it down to the bottom, and the surface is always being replenished by exchange with the atmosphere. So it's a process of drawing carbon out of the atmosphere, basically, and storing it in the deep ocean. And if there was nothing else happening, you would just suck all the CO2 out of the atmosphere, if there's really nothing else happening, and not even diffusion, I suppose. But there's a leak in this pump, and that is the ocean circulation, as we've heard earlier. And so what radiocarbon is useful for doing is giving us a measure of the mean time scale with which the carbon down here can exchange with the carbon up here and the atmosphere. So if we know how much it changed, how many years of radiocarbon decay equivalent, we might, through some theoretical calculations, get a handle on maybe what the turnover time was and maybe how much extra carbon was stored, to try to move to quantifying carbon storage to the last glacial maximum. And this is kind of what we're doing here with various different model simulations. This is some recent work that we've been doing, and some simple box models as well. So there's all these different symbols are various takes at what Fortunat showed already, an aging of the ocean, okay? So you change the ocean circulation, or you change the air-sea gas exchange in the Southern Ocean, or whatever you like, okay, to increase the radiocarbon disequilibrium and therefore the age in the deep ocean. So we're moving towards me is getting older. And as you do that, the CO2 in the atmosphere tends to come down. And that's because of this kind of like this two-box model view. You're reducing the leak, okay, and therefore you're enhancing the efficiency of the pump, and therefore you're drawing down CO2. That's the main effect. And by the way, if you change gas exchange in key parts of the ocean, okay, you have to think of a three-box model to understand this, but if you reduce the efficiency with which CO2 can get back out into the atmosphere, you also have the same effect. You age the ocean in radiocarbon terms and decrease CO2. And you can make a simple analytical sort of approximation solution to this two-box model world, and that's what I've got up here on the top. It's basically just saying that the change in atmospheric CO2, in theory, if the ocean was a two-box thing, would go like the amount of export production, how strong is the biological pump, basically, and then the rest is sort of some carbonate chemistry factors and volume scalings and so on, and how long are you letting the ocean accumulate carbon? It's quite straightforward, really. And that's this middle line here, okay, more or less. And you can see it's not too bad for two-box model. It's pretty good, which is good because this was a theory based on two-box model, and also three-box models and other GCMs. So the diamonds here are the simulations that Fortunat just showed you from Chumi et al. 2011, and then there are some other simulations. There's a spread, but they all show the same thing. You sequester carbon in the ocean, and more gets accumulated. Okay, so why am I waffling on about this? Well, if we had about 800 years aging of the glacial ocean in radiocarbon years, okay, that would be, ballpark some tens of ppm, maybe 50 ppm of CO2 change. Okay, and this is Mickey Mouse theory, but again, with Fortunat's intermediate complexity model and others as well, it's about, if you match this age, you usually get something like that, maybe 50 ppm or 35 ppm of CO2 drawdown due to the ocean ventilation change. Okay, okay, fine. So far, so good. The ocean seems to have played a role in sequestering carbon in glacials, and thus helping to keep the world cold and to have glacial states and so on in those periods. But we can also look at other things like oxygenation as a cross-check on this inference, because if we slow down the turnover and exchange with the surface ocean, and we've enhanced the respired carbon content, as we've heard earlier, you would expect to deplete the oxygen content, okay, and enhance the nutrient content. So photosynthesis for this equation, you basically have some nutrients. They come together through photosynthesis to produce some kind of carbohydrate thing and oxygen. And if you were to respire it, that is oxidize it or decay that stuff, you consume oxygen and you produce nutrients. So if we're doing more of going from here to here, we will consume oxygen. And so these are some data, most of them unpublished actually. The the stars and dots and so on, showing how a proxy for oxygen, so uranium enrichment, uranium is a redox-sensitive metal, and direct oxygen concentration estimates from this delta C13 proxy. I can't really go into all this, but these are various estimates for what oxygen in deep water might have done as a function of the age of that water as deduced from radiocarbon measurements. And you can see there's a negative scaling, which is what we'd expect, actually. And in fact, the cloud behind is the modern data. So what does the spatial gradient look like in the modern ocean? And indeed, as you go to places in the modern ocean where there's less radiocarbon, it's older water, you have less oxygen and you have more respired carbon. Okay, so our data from the LGM are showing a similar spatial gradient to the modern. That suggests that the strength of the biological pump wasn't very different. But as I showed earlier, they're also showing that on average the ocean was older, so we're allowing more time to accumulate carbon. And incidentally, for those of you who are interested, the uranium data here was measured by zapping with a laser the inside of 4M shells to measure their uranium content. Okay, so I showed you an estimate of how much CO2 could have been drawn down based on the ages, but what about the oxygen? These are very rough and very sparse oxygen data set. But if you just take the average of them, what they're suggesting for oxidation change, and you look at a whole bunch of different model simulations. These are from work by Eric Galbraith and Casimir de Laverne, where they took many, many different GCM simulations under different orbital forcings and CO2 and all sorts of stuff. And if you look at all those wild and wonderful ocean states, they all show a pretty coherent relationship between the amount of oxygen in the ocean on average and the amount of respired carbon, so the amount of accumulated carbon. Okay, so for this amount of oxygen, that would suggest we could infer the amount of respired carbon increase. And based on the same equation I showed you earlier, if we circumvent using radiocarbon and just plug in the amount of respired carbon in this equation, we get about 56 ppm reduction. Okay, these are very rough numbers, but ballpark some tens of ppm, so a significant contribution, about half potentially of glacial to glacial CO2 change. So the numbers are kind of coherent, is basically all I'm trying to say. And then you can look at other things, other proxies for nutrients, such as cadmium, calcium. Cadmium's a biolimiting nutrient, and it follows phosphate in the ocean. Carbon-13 we've already heard about. Plants tend to favor the light isotope of carbon, so if you have lots of carbon-12, that means you've got lots of recycled organic carbon, which usually goes with phosphate, as we were saying earlier. Okay, so and these show the same thing. So here's cadmium compilation for the Atlantic. For the modern, it's kind of weird. That's because they've used an interpolation that doesn't use oceanographically sensible rules. It just kind of interpolates all over the place. But nonetheless, you can see in the glacial, there's a lot more cadmium in the deep ocean than in the modern, especially in the North Atlantic. And that means there's probably more phosphate accumulating there. And if you look at carbon-13, this is the modern for the Atlantic. Okay, the north is here, the south is here. And it also, as you've seen already before, much more negative in the bottom and more positive in the top, again, suggesting an accumulation, or a shift actually, of nutrients from the surface to the deep, all consistent with the same idea of a reduced turnover of the carbon pool and an accumulation of respired carbon. Okay, transport is the same kind of deal, a little bit more interesting. There are lots of puzzles here actually to go into, but I won't have time. But this is showing a plot of water depth, okay, and protactinium thorium. This is this proxy for lateral transport with a bunch of data points for the West Atlantic, for the last glacial maximum, and for the East. And over here on the right-hand side is another sort of water depth versus protactinium thorium difference at the LGM versus modern, okay, shown with the gray lines, okay, and it has some structure. And again, consistent with the radiocarbon data I showed you, consistent with the model interpretations that Fortunato showed and so on. It looks like in the upper Atlantic, you had still active, maybe even stronger overturning, okay, so shallower core of North Atlantic output, if you like, and reduced transport at depth. For the East Atlantic, it's completely ambiguous, and for the rest of the ocean, we have no idea, I would say. Okay, so as a consistent picture emerges, it's kind of boring in a way. Maybe there's a reduced overturning of carbon and more accumulation and draws down CO2. This is an example from Juan Muglia in 2018, who did something very similar to what Fortunato showed you with their model, trying to fit these dots are data points, and they're trying to fit different circulations to those data points. And again, they also find that a model with a shallower and weaker overturning circulation best fits the data. Okay, so that's what it looks like is going on. I was inspired by Pascal's talk this morning, so I stuck this slide in. This notion of imagination tempered by observations is it's basically, I was hesitant to put any kind of conclusions like that in, but I was encouraged by this to do so, and also make it a sort of kiddies, I drew this, but it's like a children's drawing of what's going on. I would add to that imagination tempered by observation but rationalized by models is a key point for us paleoceanographers. And the key thing for the LGM is that you seem to have a shallower and weaker North Atlantic deep water. You've got biology still doing its thing, raining carbon down. You have an expanded, and that's an important point, expanded southern source deep water, okay, that moves up in the water column. And I would argue, and I've got time to go into this, but you seem to also have reduced air-sea gas exchange, both in the North Atlantic and in the Southern Ocean in particular. And both of these things contribute to drawing down atmospheric CO2. So having a weaker overturning allows you to increase the amount of carbon you can accumulate through biological rainout. But also, and it's a point I want to emphasize, as Fortune pointed out, we tend to dwell on this strong overturning, this conveyor belt part that's become a focus of many studies. But the Southern Ocean is extremely important. And in particular, I would argue that Antarctic bottom water is extremely important, in particular because it has a high disequilibrium carbon concentration, and therefore a bigger volume means a larger budget of that disequilibrium carbon. And by disequilibrium carbon, I mean carbon that accumulated from biology moving is down here, okay, it's respired, and it gets brought back up, and no, it doesn't go in the atmosphere, it goes back down, okay? So it had an opportunity, because it was at the surface, to go back in the atmosphere, but it didn't because of disequilibrium effects, poor gas exchange. And that's important. Changing the volume of Antarctic bottom water is an important thing I think it's often overlooked, because, as you can see in this plot, maybe you can't see very well, but this is a plot from Primo 2005, looking at where water came from in the ocean, where it last leaves the surface and where it first comes up. And you probably can't make it out, but down here is the Southern Ocean, and the North Atlantic's up here. But most of the water first makes contact in the Southern Ocean, and most of the water also last makes contact in the Southern Ocean. So the Southern Ocean is a key part of the ocean for feeding the interior. It isn't the most well, it is quite dynamic actually, but it isn't the AMOC, okay, but it is a hugely important reservoir, especially I would say for carbon and disequilibrium carbon in particular. And this was a point emphasized by Sarah Eggleston and Eric Galbraith recently in a modeling study where they looked at, again, a whole range of different model simulations, different worlds and ocean states and so on, and they found very clear relationships between the amount of the DIC, the amount of carbon in the ocean, and the fraction of Antarctic bottom water that's filling the deep ocean. So the more Antarctic bottom water filling the deep ocean, the more carbon is in the ocean. Okay, that's because Antarctic bottom water it has this high disequilibrium effect. It retains its carbon, doesn't give it up to the atmosphere very easily. They also showed that, of course, if you measure the global export in all these different ocean states and you multiply it by the average age of water, you also scale, sorry, the axis is gone here. This should have been respired carbon, I'm sorry for that. You also increase the respired carbon content. So those two plots I'm just using to emphasize these 2 points, the 2 shaded boxes here. This will help to draw down CO2, and especially this as well, the Antarctic bottom water, which is something that hasn't been talked about much today, but I want to emphasize. I have no idea how I'm doing for time. How much time do I have? We'll see. I'll wait for someone to stop me. Edouard is... Okay. Okay, so that was the LGM. Kind of resonating with what people have already spoken about, I suppose, a little bit, but I hope giving some slightly different perspectives on it. And this is the deglaciation. So I've just been talking about the last glacial. Okay, that's sort of here, 20-odd thousand years ago. Okay, this is a sea level curve, approximately, in glacial-eustatic terms. So this is 120 meters or so lower, if you do these huge ice sheets. Okay, and then, of course, we transition to the pre-industrial, to the Holocene, okay, where we don't have big ice sheets. And I was looking at how... Here's atmospheric CO2, okay, times going from right to left. I showed how the ocean circulation, or I argued the ocean circulation could account for some tens of ppm, maybe half of the PCO2. And that's interestingly that corresponds with what Fortunat just said, that he believes that you can only really account for this bit of the CO2 jump. In magnitude terms, that's about right, and we'll see in a minute that in dynamical terms it might also be as well, but in terms of time series. But yeah, accounting for a portion of the CO2 change. But there's other interesting features of the deglaciation, of this transition from our glacial that I just tried to give an account of to today. We didn't just go smoothly from one state to the next. there are these abrupt, more or less abrupt in different parts of the world, changes in temperature. So these are ice core proxies for temperature, showing accelerated and decelerated warming in Antarctica, and then lots of sharp wiggles in temperature in Greenland. This jump here, I think, is equivalent to, maybe order 10 degrees Celsius, so really big jumps in temperature. These are more like 2 or so. And those are also of interest. And if you look at radiocarbon again and think about, okay, I looked at the glacial state and I argued that it was a certain way, and you can look at then at how do we evolve from that state to the present. It wasn't smooth. And so up here at the top, you've got Greenland showing these abrupt cooling events in the blue, and then an abrupt warming event in the middle, okay, on the way from a glacial to the current interglacial. Down below, you have a compilation of a whole bunch of different radiocarbon records from the Atlantic, the deep Atlantic. And you can see there's quite a good degree of coherence. They all show something quite similar. There's clearly a coherence in the radiocarbon content of the deep North Atlantic and the climate anomalies you see in Greenland. That makes sense. The prima facie explanation for that is that those radiocarbon records are tracking North Atlantic overturning. And indeed, if you look at the only protactinium record that's ever plotted for the deglaciation, this red line from Jerry McManus, it shows that it argues that the transport out of the Western Atlantic did that same sort of thing. Okay, so there's a good degree of coherence that changes in ocean circulation were linked somehow, and I'm sure Garrett will talk more about this later, I suspect he will, with Greenland climate. Okay, so a role for ocean circulation in those wiggles in the North Atlantic of one type. And then if you look at mean ocean temperature, this is quite interesting, it accelerates in the blue periods and decelerates or even reverses in the red period, okay? So going from glacial to interglacial, the ocean, of course, gained heat because you had a higher CO2 and you melted ice and so on and so forth. The whole world warmed up. But there are interesting accelerations and decelerations in the mean ocean heat content. And they seem to correspond with Antarctic temperature changes, which are shown down here, and CO2, incidentally. And maybe more coherent with radiocarbon. It's a bit more noisy. We need to fix this, but this is the best we've got for now. More coherent, at least with these, than with North Atlantic radiocarbon records of ocean circulation, records of Southern Ocean and Pacific, deep Pacific radiocarbon. So it looks like the ventilation of the Southern Ocean, the deep Pacific, maybe was more linked directly to CO2 and mean ocean heat content. So a whole sort of smorgasbord of interesting links between ocean ventilation changes and regional climate changes on the deglaciation as well, which I won't go into in detail because I'm running out of time. But I wanted to at least flag them up, and I'm pretty sure that Garrett's going to talk more about those things later. So I think one thing to mention at the end of all this is sort of what is the relevance to today. My understanding this would be sort of a public lecture, so it's kind of light on science maybe. And I wanted to put in something about why do we care about this. Of course, often many things are motivated these days by the relevance to future climate change, and this is a record of atmospheric CO2 that's jumped up from about 280 pre-industrial to, well now, I made this plot years ago and I keep it because it shows very nicely how fast CO2 is going up. It's now off the graph at 420 almost. And there is some relevance to this, and that's because the ocean turnover is fundamentally linked, as we've seen, to CO2 uptake and also to heat uptake. So both heat and carbon exchanges with the atmosphere. And these are obviously very important going into the future, as Fortune already talked about. When we're putting lots of CO2 into the atmosphere, it's all going to, or most of it's going to dissolve in the ocean. But on what time scale? That depends on ocean convection. We're warming up the atmosphere as well. How fast will it warm up? Well, that also depends on heat uptake in the ocean. And both of those things are modulated by changes at the high latitudes in particular. So on this side, you've seen already this plot of anthropogenic, so human source CO2 invading, the hot colors invading the ocean. This is the Atlantic, the Pacific, and the Indian Ocean. The rate at which we mix that into the ocean depends on turnover. And also the rate at which heat can accumulate in the atmosphere versus going into the ocean also depends on convection at high latitudes. So this is a plot showing how decades with, so there's temperature, mixed layer depth anomaly for different time periods, and it's for the southern hemisphere and the northern hemisphere high latitudes. But this study by Mailodal shows how decades with slower global warming tend to coincide with less convection at high latitudes, and that's because the tropics are continually taking up the excess heat, and they tend to vent it at high latitudes where you have convection. If you have less convection, you can't vent it as much, and so you store heat. And this sort of thing is quite interesting. As Fortunet pointed out, the effects of future change in circulation are probably quite small in the grand scheme of things. But the way that I look at this is that those small changes, so is it some tens of ppm through a ventilation change, or a few, a slightly slower rate of warming and so on over some decades due to convection changes, could be important because, for example, if we're aiming for 1.5 degrees or 2 degrees Celsius warming, and we've only got 20 years of current emissions to achieve that, these small changes start to become important in terms of the time we have. So they're equivalent to maybe a decade or so of extra time or less time. If you accelerate warming or decelerate it, or you take up more CO2 or less, it's not going to overwhelm the anthropogenic effects, but it might buy us or lose us time, if you like. So they're still important, I think, these relatively small changes. And that's all really I want to say. By way of summary, I guess one key point is that the global overturning circulation has changed significantly in the past. We don't know much about the transport, but we can say that it changed, and we can say that it changed the carbon retention capacity of the ocean in particular. So, for example, at the last glacial maximum, it looks as though maybe 50% of the total change could be accounted for by ocean ventilation changes. It also seems, I didn't go much into this, but you'll probably see more of it later, that the ocean circulation also contributes to millennial scale pulses in CO2 and regional climate on deglaciation. And I would argue that such examples of ocean circulation changes from the relatively distant past are really our only empirical evidence for such long-term and large-scale changes. And for that reason, even though it's very difficult to get a handle on what's going on, knowing something about it is still quite informed, and it still provides an important training ground, if you like, for our understanding of the stability properties of the ocean circulation and the different modes of ocean circulation that you can have. I've been to meetings, and more so in the past, and you often have some discussions with physical oceanographers who are saying, "Oh, all you oceanographer folks, you don't, what have you ever done for us?" And it's true, probably not much in terms of detailed understanding of how the ocean circulates and why and so on, the drivers and everything. That comes from other studies. But probably we'll be spending less time even thinking about a lot of this if we didn't have evidence for these changes in the past. So it's an important motivator at the very least. With that, I'll stop. Thanks.